So the title of this talk was originally Advanced Topics in Portfolio Optimization, but I'm not an expert in portfolio models as much as Gabor is. So I will not tell you any new optimization models or any new portfolio knowledge. Instead, I wanted to focus on the sort of more practical topics of how to do things with Mosek, so that maybe when you go home, you are ready to take your portfolio optimization models and implement them in Mosek. And also, along the way, I will kind of trace Gabor's talk with some extra details, and along the way try to show how Mosek is performing and what's going on, and to give you a little bit insight into how the optimizer actually works and how you can work with it, so that you have some tools, just a little bit of insight into what's going on that can save a lot of frustration compared to if you try to use the tool as just a black box and know completely nothing about it. So that's the only point of the talk. And if there is anything advanced about the talk, is that if we lose network, then I can't run it, because I'm actually going to show some code running live, and then we'll have to pray. Right, so I'm using the latest Mosek version, and the plan is that we will go through this simple mean variance optimization, and I'll show how to work with it and what's going on and how things are done, how to debug it if you have to debug it. Then we'll again discuss the factor model and show a real example of that, and use it as a base to show how to analyze the solution and how to re-optimize and do other things with the optimizer, what can go wrong when you're working with actual data, and then talk a little bit about the mixed integer optimizer, even though much of that was discussed in the questions after the last session, but still we'll try. Okay, so we now go to our first model. This was the model that Gabor introduced. Sigma is a positive definite covariance matrix, which appears in this quadratic risk bound, and otherwise there are some constraints. I mean, you can always choose others, but this is the sort of one of the basic ways to do this. And you're optimizing the expected return on this portfolio. Gabor already provided some data in the last talk with some portfolio with 8 assets and certain parameters that you have over there. And then he explained how to cast it into conic form. So now I'm just reminding you that we need to find the factorization of the covariance matrix in this form G times G transpose. The Cholesky factorization is fine, but any factorization is just as good, and some are much better, as we will see later. And then when you have it, then a little bit of math shows how to write your risk constraint as a bound on the norm of some vector, in this case, this G transpose X. And if we know that, this is just a reminder from the previous talk, then we can go ahead, and since we don't have any better plans, then I'll just compute this Cholesky factorization. The Cholesky factorization is some matrix, lower triangular matrix, and just to reassure you, I've actually checked over there that S equals G times G transpose, at least up to 10 to the minus 17. So by the way, this is slide number 3 or something, and we are already into sort of floating point arithmetic considerations where you have to remember that 10 to the minus 17 or something like that can show up where you expected equality mathematically, right? But that's life. Okay, and Gabor also introduced this second order cone, which is one of the sets in Mosek, the domains you can use in your conic constraints. And that means that we can just express our bound as a membership in this cone of this stacked vector consisting of gamma sort of on one side and G transpose X on the other side. Okay. By the way, if you have any questions at any point, just feel free to interrupt and ask if it's too fast or too slow or anything. Yeah, so that is the conic form that Gabor also mentioned, where I replaced the quadratic constraint with a conic constraint, and now I can go ahead and construct the model. I'll just start by making an empty model, And then, of course, every constraint has a translation into something in Fusion. I have a positive variable of length as many as I had assets. I have the sum that equals 1. These are weights. It's a linear constraint. I have the conic constraint for the risk. And eventually I have some objective, right? I'm maximizing a function, a linear function of x. And all this put together, I've constructed this model M, which now I'm going at the beginning of the code over there to solve, and then see the solution I've got. So I not only solve the model, but I also the first thing I do after I solve a model, I see like what is the answer. Is the model feasible? Is it infeasible? Has it been solved successfully? Is the solution status optimal, or is it unknown, or is there some indication from the solver that there was some numerical issue or anything else like that? It's always a good thing to check. Here I'm doing it in just a very quick, this very quick form of just printing out the problem status. But of course, I would recommend everyone to do this more carefully if you want to know what exactly happened in the solve. And then I get the solution, and here it is. Okay, the solution maybe itself is not so extremely interesting in this case. But another thing you should do, and I always encourage everyone to do when they have a solution, is to actually check that it works. Because ultimately it's the user's sort of thing. Would you trust Mosek to give you the right solution? Well, I hope you would eventually, but it's also a good idea to check yourself that what you get makes sense in the context of your problem that you formulated, just to convince yourself and to see that everything's right. And indeed, they seem to add up to 1, at least up to a tiny, tiny violation. The risk seems to be correct. I've even, to reassure you, even more computed the risk using the quadratic form that we had originally. And all the x's are indeed non-negative, right? So we would conclude that this was a successfully solved problem with a good solution that matches all the constraints and is usable in the context of the original problem we had. Now, when I was making this model for the slides, even though I'm supposedly an optimization specialist in Mosek, I made around 5 errors and things didn't work as they should, and I was getting crazy answers. And so at some point it's good to know what to do to debug your model, because it's like with every other form of programming, there will be bugs, right? In your model or in your implementation, or who knows. So there are some tools to help you with that. The first one is that you can just write the model to a file, and then you get a file that summarizes how big the problem dimensions are, what the objective was, what the constraints were. Now you see there is a budget constraint that says the sum of all these things, and then there is a 1 in the beginning, adds up to 1. And then there is some second order cone constraint with certain expressions that look like G transpose times X, if you remember the data from G. So at least you can visually check if things are more or less okay, right? So you can check this and see if it sort of matches your expectations. Another interesting thing to know is how to actually evaluate if the solver was doing a good job during the solve. And this you can do by looking at the log output from the solver. The log output does more or less as a similar introduction. It tells you what the problem dimensions were. Okay, I had 1 cone. That sounds reasonable. There was supposed to be 1 cone. So maybe that's okay. Then there is a summary of the pre-solve, which is like a pre-step before the actual problem gets sent to the optimizer. And then there is a summary of the optimization process. Now maybe I'll take 1 minute to explain what's going on here roughly. So the interior point optimizer, you can think of it as it's converging to the optimal solution in a number of steps. So these residuals here in the first 3 columns is how close you are. You can think of it as a measure of how close you are to the optimal point now. So these things should be converging to 0, which they nicely are. Then there are the objectives, the primal and dual objective. Well, they should be converging to one another, which they do. And then in the last column, you just have the runtime. So this looks okay, because it seems like everything converged nicely. And probably the most important ever part of this is the solution summary, where you can see, right, is the primal and dual objective roughly the same? Is the solution not too huge? NRM stands for norm. If the solution values are humongous, then maybe something was numerically not great. And then there are the violations, which is by how much the constraints are violated. We have already seen that no matter what you do in floating point arithmetic, you are never exactly spot on, but maybe 10 to the 9th, like here, away. So that would be sort of on the level of numerical precision. So everything looks good about this. But if the interior solution summary is more shaky, has bigger violations, the primal and dual objectives don't matter, then you kind of have an indication that maybe something should be fixed about the numerical properties of the model, or that there is something more fishy going on. Okay, so that was a kind of quick tour of how you would work with this simple model. Of course, there is this one thing that was already asked, and people sometimes ask, why would I even, in this context, bother with this conversion to the conic form? Why don't I use something like cvxpi, and just cvxpi allows you to write the risk constraint as just an explicit quadratic constraint. But of course you can. There is no problem with that. There are many modeling tools that allow that, and that still allow you to use Mosek. That's perfectly fine. However, you have to be aware that first of all, cvxpi still has to perform this factorization in order to feed the problem into Mosek, and also that the problem you get might not exactly be as readable and, like Erling already mentioned, and as close to the problem you actually formulated, because these tools perform various other reformulations that maybe you have no control over. So yeah, I don't know if you remember what was in this other problem, but this objective, for example, over there does not in any case remind you of this M transpose times X that you originally wrote, right? Okay, so now let me jump to this other part, in which I will take a big, actual big portfolio model from the real world, and this is something like X is the vector consisting of assets and one last position for cache. It's just how it's formulated, and then therefore this balancing constraint is now that everything adds up to 0. In particular, we allowed short selling here, and there are some bounds on the traits, and there are some other that I will not go into, but you can throw in many other bounds. These were some bounds on sectors or contributions of various sectors on the market. Just some linear constraints in any case. And then there is this risk bound, which has the factor form, and it bounds the risk of the target portfolio you would get from the original holdings and your new inputs. Right. So I've got this data all set up somewhere here, and it actually consists of like almost 4,000 assets, but only 40 factors. So it's a kind of I guess a reasonable sized factor model. Right. So we've already discussed many times how to produce this linear part. It's sort of a direct translation of what's there written in LaTeX up on the slide, and then we have this risk, right? So of course, if we follow the usual path, then we just compute this risk matrix sigma. It's a matrix of dimensions 4,000 by 4,000. And then if we follow the path from before, then we also factorize it to compute this Cholesky factorization. Yeah, and the matrix is not positive definite, is the exception here. But of course, you know the matrix is positive semi-definite. It's because that's how you constructed it. So what's wrong with this matrix? Why is it not allowing itself to be factorized? And the answer, if you compute the eigenvalues, is that the first two eigenvalues are a tiny little bit negative, because the Cholesky factorization of a big matrix of this size is kind of what you might expect if the matrix is only positive semi-definite, then, okay, a tiny rounding here and there, and when you were doing it on 4,000 rows, then eventually you end up with this rounding error, which if you just want to continue from here, there is not much you can do. Usually this sort of thing is fixed by adding a tiny perturbation to the diagonal, so that it actually factorizes. To just address your cvxpi question, when I saw this initially, this model, it was implemented in cvxpi, and then cvxpi factorizes a bit differently, and it actually goes into an infinite loop on this model, trying to produce the factorization of the big covariance matrix. So different things can happen. But now we have sort of an approximate factorization because we perturbed a tiny bit, and we can construct eventually the risk constraint, add it to our basic model, which we had before with the linear constraints, and if we are lucky, then start solving. Right? Yeah, it drills a little bit, but here we go. This has about 4,000 constraints, which sounds fair for this number of assets, and it started solving. And while I was talking, it solved in 15.2 seconds over there. And the solution looks reasonably nice. Things match each other. The violations are not too big compared to how big the solution is, and we would sort of say everything went fine. How many variables we had? Well, we had one variable for each asset, roughly. And then we have these extra variables because that's sort of how Fusion models the conic constraint. It has to add some slacks. So we had about double that many. So, but the essence was 4,000 variables and about 4,000 constraints or entries in the risk constraint, right? And now let's do this thing that Gabor advertised we should do at this point. So to exploit the factor model we already had. So instead of computing the factorization of this big matrix sigma, which was a bit shaky as we saw, then we just compute the factorization of the small factor covariance matrix, which in our problem is of dimension 40 by 40, or was it 43 maybe? And that is a much more sort of numerically stable operation because the matrix is very small. And this is what we do. We compute the Cholesky of the factor covariance matrix, and we use this formula, which essentially allows us to, we almost have the factorization. There was no need to compute the full sigma matrix. We almost have the factorization already. It's just a tiny step of factorizing the small matrix, and we are already there. And we construct this new model, the factor model, and this one we can also solve. This one you can also solve. It's kind of a similar size, you would think. It's got 4,000 constraints and the same number of variables almost. It's not one cone. There's nothing different over here, right? Except that it solves in 0.27 seconds for me here, whereas the previous one took 15 seconds. And the solution actually, if you would compare, it's a little bit better here, but kind of the same, almost the same quality. Okay, so just to summarize what happened here and is that we solved the problem, and if you want, we can the usual thing we can do after we solve the problem is check various things. For example, check that we match the risk, okay, and see roughly how big the solution is. This model is not a weighted model, so it's in terms of actual monetary values, say, for example. So the numbers go into thousands and millions rather than add up to one. And we can go ahead, analyze the solution, see what we got. Okay, these are the traits that we're getting. Some of them are kind of substantial, but a lot of them seem to be concentrated around 0, which is often the case and something you might want to investigate. How many are there that actually make a difference here? Well, there were 4,000 assets, but only like 100 of them are more than 1 promille of the total investment that you're making. So maybe there are things you want to analyze about this solution and see what's going on. Of course, the point is that a typical solution actually consists almost of zeros. Here's a substantial entry, right? But otherwise, these things are almost zeros. If you want to clean them up afterwards, it's sort of up to the user what to do about these things. If you want to do something about these things, because I guess you don't want to. If you're investing a million, then you are not going to put 10 to the minus 8 into any particular position. That's a typical issue that also appears in connection with this. So you could say force these positions to 0 and then reoptimize, or do whatever other post-processing you want. I will do this here. I will choose the positions I want to ignore. Those are the very small ones. And then I will just constrain the traits variable to ignore them, to set them equal to 0 and sort of reoptimize on the fly and see what I'm getting now. Now I'm getting something that looks more either it's 0 or it's something essential, right? And all these kinds of things that you want to do belong to the sort of post-processing of the solution. Okay, so the quick summary of this is that we made this full model where we multiplied all the data together into the sigma matrix, which then had to be factorized again, either factorized by ourselves or by cvxpi or by the solver if it was another type of input. And that this factorization can be problematic, but even more problematically, we created a very dense problem that takes a lot of time to solve. Whereas we had the factor structure, we were able to use it ourselves to create a much smaller version of the problem. And while in the first model, I mean, if you really multiply these things together and form this quadratic problem, you could just use a QP solver. That's what you would do if you were using a QP solver, and the conic form is sort of not any, it doesn't seem to bring anything substantial in here. You had a QP, you could have solved it as a QP. Whereas for the factor model, the conic form is really essential in order to formulate the problem even. Yeah, the last thing that comes up here is that, and maybe this we also touched upon a little bit, is that it doesn't really matter how many constraints, or it doesn't matter so much how many constraints or variables your problem has. What matters most is what is the sparsity pattern of the problem, or what is the density of the constraint matrix. So we usually depict it by having the constraints on the vertical and the variables on the horizontal axis, and every blue point is a non-zero in this equation system that appears inside the solver when you feed in the problem, right? And here the big triangle, this is this whole Cholesky factorization of the big sigma matrix. This is full of non-zeros. Whereas in the factor model above, there is just this tiny little strip, essentially. That's the factorization of the factor covariance matrix only, that was of size 40, right? Times the number of variables, instead of the number of variables times the number of variables, which is sort of a couple thousand times worse. And we also saw a performance that was 50 or 100 times worse because of that. So this is more of a key here. So now you're sort of, maybe you kind of have the idea how to a little bit work with data with Mosek. And in the last part, I'll just mention very quickly the mixed integer optimizer. As I said, some of what I want to say was discussed in the questions after the last talk. So the mixed integer optimizer, or the mixed integer optimization, of course, is an extension of what we did here, where you allow some variables to only take integer values. And in particular, one of the most interesting cases is the binary case, where you only allow them to have values restricted to either 0 or 1. Applications of this is that you might actually be counting things, so that's what you need the integers for. And especially for binary variables, the main applications is to consider the binary variable as a switch that is either on or off and decides if some event or indicates if some event happened or didn't happen, or happens or doesn't happen, which can be used to model implications and functions that are only defined piecewise. and other such things that depend on checking if some condition holds or not. And as we already discussed, mixed integer problems are both in theory and in practice hard, much harder than their convex continuous versions. So let's have a look at how we could extend our big factor model with the cardinality constraint. So already last time we saw that although we have 4,000 assets, then the optimizer finds, well, around 100 or then 50 or whatever it was to be sort of receive an essential investment. So we could just try to bound it with the mixed integer optimizer, just bound it explicitly when we construct the model. So I'd like to have that at least, that at most, I don't know, 100 traits are non-zero, and the rest are zero. So this is what we do with these switches, the binary switches. We introduce a binary variable. For every asset, we have a new binary variable that will intentionally be 1 if we are supposed to trade that asset and 0 otherwise. And as long as we know a good common bound for all the traits, which we kind of know because we already solved the continuous problem, or we may have another reason to know it, then this switching is just expressed by a pair of linear inequalities. So if z is 0, it forces your x to be 0. If z is non-zero, in this case 1, well, then the constraint is redundant because we already know that x is between minus m and m. So in other words, we can with this linear expression formulate this counting principle that the zi's count the x's we are investing in. And like before, we can take the original factor model and just make this extension explicitly. We define the binary variables. I chose, in this case, to define the parameter, the big M, and the cardinality bound as parameters because I want to solve it a few times with different values of k. And then I'm adding the linear equalities and the actual cardinality bound. All this that we had on the previous slide, again, is more or less the same syntax as we had before. Yeah, so we already discussed that mixed integer models are much harder to solve, and in this case I'm going to give myself 80 seconds to find a portfolio with at most 100 cardinality bound on the number of assets I'm going to invest in. And now that gives me 80 seconds actually, I think, yeah. That gives me 80 seconds to explain the difference between the mixed integer optimizer and the continuous optimizer. So, like I said, the continuous optimizer in a sequence of steps converges to the optimal solution, which is, at least in the most non-degenerate case, let's say, it's a unique, because we had a convex, let's say, strictly convex problem. So you can follow the central path and get there. The mixed integer problem is more complicated because the set of points you're looking at is discrete. You have these binary variables and the product of them. It's a discrete set, so you can't really converge to any of them because you don't know which one. That's the whole point. So what you do instead is to try to bound the region in which you are looking for the optimal point. And that bounding this region you can think of is like sampling which of these binary variables should have value 0, which should have value 1, and trying to resolve for the rest. That's what happens in these possibly many branches in which in each of them we solve some continuous problem and use it to bound the region we're in. The region we are in is, roughly speaking, bounded by the best solution we found so far. This is its objective value. And the best bound that we can prove by this process of cutting down the region. And these things, when they converge, then we are at the optimal point. So here, as you can see, after these 80 seconds I was talking, we've ended up knowing that we have a solution with objective value 5.61 million, and the best bound we could get to potentially is 5.69 million, which gives us this relative gap of 1.4%. So we are guaranteed to be 1.4% away from the optimum. Yeah, so again, I would, if I was doing it, I would inspect the solution and check that I actually have In the z vector, I actually have 100 non-zeros, so I've chosen to invest into 100 trades and not more. Of course, now the next thing I would do is to look at the actual investments, right? The x values, and you see of those I have 130, whereas I was supposed to have 100. And the point, of course, is the same as always, namely that some of them, well, they are not strictly speaking zero in floating point arithmetic, right? But they are still within the tolerance for being a solution, a solution with tiny violations in floating point. So there are some things again to be careful about. If you are extremely careful, then up there I shouldn't even write that I'm comparing z to 1 in floating point. I should maybe have written something like z is bigger than 0.9, just because it can still have a floating point value. That is not exactly 1. But we understand, at least now that we checked what's going on here, we understand what's going on. It's not like the z values lie. It's just that something is almost 0. Yeah, so because we already mentioned it's hard, the mixed integer world is hard, then there is an extreme amount of tuning you could possibly do. We mentioned this before, that in the continuous optimizer, I wouldn't try to tweak the parameters too much when I'm using it. But in the MIP optimizer, it's sometimes extremely useful and actually necessary to turn off or rather on various kinds of heuristics, make various choices of how the optimizer should proceed. As for the termination, I had this time limit, which was great because I tested it already 3 times and I knew it's going to work like I expect, but it would be more platform independent or machine independent to settle that you terminate when this relative gap between the best solution and the actual bound is bounded by some value. Or you could terminate if you already found 3 solutions, then you're not waiting for the 4th improvement, but you stop, and so on. Another important technique related to the warm start in the continuous optimizer, here it's much more important that it's always, or very often, a good idea to specify a good starting point for the optimizer to start, because that can already mean that you can cut off a large chunk of this search space that you're going through if you already know some reasonably good solution. And finally, like Erling said, just reiterate this, that the algorithm is very sensitive to data, not just to the structure of a problem. You can keep the structure of the problem the same, but small variations in the data can lead to big changes in solution time, or if you get a solution or not in reasonable time. So there is a lot more sort of tweaking for you as a user when you're using the mixed integer optimizer than when you're using the conic optimizer. So as an example of that, let me now, before I solved this problem with at most 100 assets, and there inside the model there is still sitting a solution with at most 100 investments. Surely this solution is a feasible point if I now want at most 150 investments, right? It's sort of even more sharp or restrictive. So let me now use it to find a solution with 150 positions, and this time try to terminate upon reaching this relative gap of some level, like 0.005. I'm using because I didn't change the model, so the solution is still there. I'm just re-optimizing. That's another useful thing you can do. I'm just re-optimizing with the same model that contains the solution that we already found before. Yeah, and we should hopefully see that in a moment that I'm actually doing that. In fact, we don't remember, but it's this objective here. This is exactly the objective of the previous solution we had over there, and you see how lucky we are. Actually, I think we are optimal, right? We are optimal. Now here, we found the optimal solution. The gap is 0, that the objective matches the bound. Even though we had a problem of the same structure, but we found the solution much faster for this slightly different data. And here you can see that we actually employed this solution that was already there. So the construct solution is the solution, is from this feasible point that was already there. So whether this helped or whether it helped that I had a different bound and it was numerically different than before, that's an open question for the purpose of this talk. But as you can see, it was a small variation and now. Okay, I'm actually finishing. So to summarize these talks in the morning, there are some advantages to the conic form. The problem is convex by construction. You can easily write a quadratic form that is not positive definite and try to feed it to a convex solver, but you cannot write a conic problem that is not convex and try to feed it into Mosek because just by construction everything is convex. For many problems like the factor model, it's a lot more effective because you already have the data that is just about suitable for the conic form. For some types of constraints, this is the only choice, the conic form. The theory is nice and it works very well. The topic we have completely not touched upon is that in the convex case you have duality, very nice duality theory. Dual solution is what you might know as shadow prices, or it appears as a constraint attribution in some scenarios in portfolio optimization, but it also gives you infeasibility certificates. It gives you the way to detect which constraints are binding and all other kinds of things. And as I said, everything here was Python Fusion, but there is C++ Fusion, Java Fusion, if you like, .NET Fusion. There are other APIs that are more matrix or low-level oriented, but you can still use them. And there are a lot of other modeling languages similar to cvxpi that all belong to this world of DCP, as people sometimes call it, disciplined convex programming. It's disciplined in the sense that you have to be able to phrase your convex problem in this specific format. That sort of, for the first, proves convexity by construction and then can be fed to a solver. So it's not just Mosek, but there is a kind of a bigger ecosystem around it. And this is where I would stop here. Thank you.